The electron, the muon, the tau, and their respective neutrinos make up the leptons. All the leptons are stable except for the muon and the tau. The electron and the electron neutrino make up matter. The quarks are made up of 6 flavors of particle. The down, the strange, and the bottom have a charge of -1/3. The up, the charm, and the top have a charge of +2/3. Only the up and the down make up normal matter, that being protons and neutrons. The gluon is the force carrier for the strong force, and it glues together the quarks and neutrons and protons, and holds the nucleus together. The photon is the carrier particle of the electromagnetic force, which accounts for light propagation and how a magnet can pick up iron filings. The W and Z bosons are the exchange particles for the weak force, and are responsible for energy production in the Sun and radioactive beta decay. The Higgs boson accounts for the Higgs mechanism, and although it is as of yet undiscovered, it is used in many calculations.
Protons enter the linear accelerator, where they are accelerated by an electric field. This increases the speed of the protons to 1/3 of the speed of light. The protons are then fed into 4 booster rings, 157 meters in circumference, where a pulsating electric field accelerates the packets of protons to approximately 90% of the speed of light. On leaving the booster, the 4 packets recombine and enter the proton synchrotron. After circulating for just 1.2 seconds, the protons are now travelling at 99.9% of the speed of light, and because they can't go any faster, the increasing energy of the protons means they gain in mass. They now go into the superproton synchrotron with a circumference of 7 kilometers, followed by the Large Hadron Collider itself with a circumference of 27 kilometers. This consists of 2 tubes with proton beams travelling in opposite directions. After 30 minutes of circling, each proton now has 7 tera-electron volts of energy. And now the proton beams meet at one of the 4 detectors in the collider. The collision produces energy, along with particles and antiparticles. Scientists hope one of these particles produced will be the Higgs boson. However, it is proving to be difficult to detect because it can decay long before it reaches the detectors. Several regions have been eliminated in terms of the possible mass range of the Higgs, and scientists think the Higgs will most likely have a mass of around 125. The Higgs field is a quantum field that fills all of space, and it is what gives particles their mass. A good way of thinking of this field is as a liquid that acts more or less viscous at any point in space, depending on each particle travelling through it. In this experiment, the coin, representing a particle, travels more slowly through a viscous liquid. The more viscous the liquid acting on the particle, the more mass the particle has.